Hello everyone. In this video we are going to talk about the PID controllers and how they can be realized in the industrial applications. So we will focus on the industrial realization of the PID controllers in this video. We will be first starting with talking about the derivative action and how we can make the derivative action being more smooth. So the objective here is to reduce the spikes due to the sudden changes that we might have in the references. And it might be because we have since we have the derivative action for our PID controller, when there are sudden changes and in the reference signal there would be some spikes, and we want to reduce these spikes. Instead of using the transfer function for the practical PID controller that you can see over here, this is the standard practical PID controller with three actions: proportional, derivative, and integral. Instead of using this, we will apply the derivative action directly on the output. So you can see that here we have the actual output. It will be, we also consider the noise here. It will be used as the input to the derivative action. For the proportional and the integral part, for the PI part of the controller, we will still use the error signal. So reference minus the output, which is the error, we also have the noise here. So for the PI part, we will use the error signal. For the derivative action, instead the output will be directly used as the input. So we'll have kps plus ki over s for the PID controller, and then we have the derivative action in the form of kds over 1 plus tas, and their output are being summed to each other. So we'll have plus here, minus here, and then the u signal, which is the input to the controller, will be generated. Let's see how this affects the response of the system. So let's consider the mass spring damper system with the transfer function given here. We have a second order system with s squared plus 10s plus 20 at the denominator and 1 at the numerator. A PID controller has been designed with Kp equal to 50, Ki equal to 350, and so this one of these Ki's will be indeed Kd. We can get it from here. Kd is equal to 50. Kp is equal to 350. Let me just fix this. So 350 is what we have for Kp. Kd is equal to 50 and Ki is equal to 300. We can see that this controller has an integrator because we have the pole at the origin, and it has zeros at -2 and -5. And in order to obtain the practical implementation for the PID controller, we also add a pole at s equal to -1 over t of a, which is at -25. So this is in order to make the PID controller realistic, not an ideal one. And here you can see the transfer function, the final transfer function for the PID controller, for the practical PID controller. So we have 50 s squared plus 350 s plus 300 over s times 1 plus 0.04 s. We now want to show the results for the standard implementation and also inserting the derivative action on the output. So indeed, smoothing the derivative action. Here you can see the results indeed. In the figure above, we have the output, which is the position. What you see in dashed line is the reference signal. So we have a step input in it, which is being considered at the time instance of 1 second. We have the reference. With the standard realization of the practical PID controller, we will get the output in the form of this blue curve. You can see that we have some overshoot here. And the third indeed curve that you see is the one which is obtained by the smooth derivative action. So when we have the smooth derivative action, you can see that the response is indeed more smooth, and we don't have the spike kind of overshoot that we had with the standard one. So in the case of smooth derivative action, you see that the output kind of changes smoothly. Still there is some overshoot, but you can see that it is not sharp. Yeah. And here you can see the control variable, or U of t, for the standard case and for the smooth derivative action. You can see that in the standard case, the control signal has a big jump, while for the smooth derivative case, the amount of the jump is much smaller. So the spike here is indeed weakened. This is what we get with the smooth derivative action for the practical PID controller. The next point regarding the industrial realization of the PID controllers is regarding the Windup problem. In the practical cases, the control variable is saturated. You can see it over here. This is because we don't want our actuators to be damaged. If you have a DC motor which receives the input, the control signal as its input, you don't want to burn the motor by applying excessive voltage at the input. But now, on the other hand, if the control variable is equal to U, so we have the control variable, the actual control action which will be provided to the actuator will be called as V, and you can see the relation over here. If U is between minus US and plus US, then the output will be the same as the input. But if it goes beyond those values, the output will be saturated. So it will be bounded between minus US and plus US. And in between, indeed, it will follow the actual input. So we can say that here we have the input, which is U, the control signal generated by the controller, and here we have V, which is the actual input to the actuator. Okay, so here we have US minus US, US minus US. And we say that plus minus US are the bounds for the control variable. Now, let's see how this will be. This might create problems. Yeah. In many cases, this might not be a big problem, especially if the control signal which is generated when U is already between plus minus US, then there will be no problem at all. Yeah. But if it goes beyond these values, there would be some problems. So when we use a proportional or a PD controller, for instance, instead of the complete PID controller, the control variable will only be limited and possibly will lead to slower convergence times. The problem actually arises when we have the integral action. When we have the integral action present in the controller, the controller will think of increasing the control action by integration. But only U will increase because the controller is generating the U as the signal. And the actual signal that will be provided to the actuator, U, will stop once it reaches US value. So when U reaches US, V will stop and it will be saturated. Then, as a result, the integral term will increase too much because the controller will think that the amount of the control signal which is generated is not enough, so it will try to increase it without knowing that it is already saturated and it's the maximum value. Yeah. And once the system output will be back to the set point, so the eventually when the output of the system goes back to the set point, the integral part of U will still keep pushing the output in the same direction until the integral term fades. And this can usually cause large oscillations. So these are the in its effects, the drawbacks that we want to get rid of. Large oscillations and long settling times. So these are what we get when we use the practical PID controller and we have the saturation in the practical case. Yeah? So now if an integral action is present with a rather large coefficient Ki and the control variable can reach the saturation bounds during normal operation, we would need to use an anti-Windup scheme. And we will see in the next slide what the anti-Windup scheme is indeed, yeah, and how it works. You can see here the schematic for the PID controller with the anti-Windup scheme. And we also have the smooth derivative part indeed. Smooth derivative action, which is presented here, and it receives the input directly from the output, not from the error signal. For the anti-Windup scheme, you can see that we have the configuration a little bit different than what we had for the PI controller. So if you compare this with the PI action or with the PI controller, you can see the difference. The integral action receives the input from the output of the saturation part indeed, and its output is being added to the Kp times the error signal. So we have the error signal here. Here we have Kp times the error signal, and then it is being added to the output of the integral action, which is fed into the saturation element. And then the output is being added indeed with the negative sign to the output of the derivative action, and it gives us the control command, which is eventually being passes through the saturation part and then is applied to the actuator. The scheme which is shown here is only suitable for the PI or PID controllers, but it would be also possible to generalize it for any controller with integral action. So whenever the integral action is present, you can kind of think of this scheme. Yeah? For the integral action, you just, instead of providing the error directly as the input and then summing its output with what you get from the rest of the controller, you kind of provide the output from the saturation element as the input of the integral action and then add it to its output to the control signal coming from the rest of the controller. As an example, you can consider the controlling the previously mentioned mass spring damper with a PI controller where we have Kp equal to 30, Ki equal to 200, and a saturation bond at plus minus 22. And here we will see the effect of the anti-Windup scheme. Again, in dashed line, we see the reference signal, and here we have in the upper part we have the output, which is the position. In blue, you can see the PI controller without anti-Windup, and it gives us this output that you see here in blue, and the one in red gives us the output using the controller, the PI controller with the anti-Windup scheme. And I guess you can see the difference, especially here. So with the blue one without anti-windup, you can see that it takes a long time to settle back to the actual value that we are looking for, yeah, to the final value. But while with the anti-windup, it takes much less in order to go back to the, and you can see it here. So the red one, it goes quickly, it's much quicker than the case where there is no anti-windup. In the second graph here, we can see the control variable u of t, where we have no anti-windup. So without anti-windup, with the regular, let's say, PI controller, what we are expecting is the blue one. So this is what the controller is generating, the blue signal. And what we get actually and feed to the actuator is shown in red. And you can see that it is saturated at plus 22. Yeah? And it waits until the control action goes back, and then it will be the same as the expected one will be the same as the saturated one. In the last graph here, you can see the control variable u when we have the anti-windup scheme. And if you compare it with the previous graph here, you see that in this case the blue one, which is the expected one, becomes the same as the saturated one quickly. So for a short time it goes beyond the saturation limits, but after a very short time it goes back to and falls in between the two saturation limits. And that's why here we also see that the actual output of the system goes its settling time becomes smaller, yeah, we can say, compared to the case in which we don't have the windup effect or scheme. Alright, so that's all for this video. I hope you have got the idea about the smooth derivative action for the PID controller, and also the anti-windup scheme or effect that we can have for the PID controllers. I hope this information will be useful for you in doing the lab assignment. Thank you for watching, and see you in the next video.